Hey everyone, I want to show you a little science project I put together last night. Nothing too crazy, but kind of entertaining nonetheless. It is a model railroad. As you can see, it is on the dining room table, and it is circling out around the Christmas decorations. So it's not going to be here long. But anyway, this is not unlike most model railroads, other than the fact that it's been digitized. So it is digitally controlled. I put the circuits together and built the program that runs it. It's all relatively easy to do, but it's kind of fun and entertaining nonetheless. I'm going to show you how that works, and then I'm going to show you how I made it even better yet. So anyway, let's take a look at the web interface of this thing. You can see it on the screen here. It's pretty straightforward. It is a slider for the actual speed of the train, right? We don't have to turn left or right. It goes where the rails go. And then it's the directional button, so forward and backwards. That's all there is to it. If we wanted to make the train go, you can slide the slider up. Train starts to move. If we want to change the direction, we can toggle the directional slider, and we can, back the thing back up and go from there. So pretty straightforward, or at least the functionality is. This will work. This is actually on my laptop. This is running on my laptop. I can have this same screen available on a mobile phone, tablet, you name it. So it can be controlled from anywhere. Let's take a look at how the electronics are built out, and then take a look at the software. And last but not least, we may actually integrate this with something else to make it even cooler yet. So stick with me. So most model railroads come with a variable transformer. You can see this is the one this came with. I have it turned the whole way up to 100 because we're actually going to control the voltage somewhere else. I just needed the thing as the power supply. I have it connected with this speaker wire, which I'm sure there's about 10 different things wrong with doing that, but it works for what we're doing here. The motor driver can be seen here, has a little heat sink on to dissipate the heat because it does have a little current going through it. The red wire, which circles out around and plugs into our track, that is the control wire. Typically the OEM setup, if you will, has that red wire connected over to the transformer. The controls and the brains of the operation is actually this, the Raspberry Pi computer. Now this is about the size of a credit card, pretty slick little control device if you've not heard of it or seen it before. Mine is actually mounted upside down on a DIN rail mountable fixture. It has a bunch of screw terminals. As you can see, that made it really easy to get this stuff connected, so that's why it is the way it is. You can see these control wires that come from the Raspberry Pi over to the motor controller. The blue wire is using a pulse width modulated signal to adjust the voltage that goes to the rails, to the train, and to the train's motor ultimately. And then there's the yellow and the green wire, which control the direction. So if the yellow wire is a 1, it goes forward. If the green wire is a 1, it goes in reverse. If they're both 1s, something broke. We'll take a look at that in the software next. While controlling the train from the web interface or from a mobile phone was pretty cool, I wanted to take it one step further and integrate with something else. That something else is my DX80. I have a third button configured on the touch panel here. If you open it up, I added a slider and added a toggle button. Labeled them accordingly. The slider obviously is the speed and the toggle is the direction. The slider can be used to control the speed. If I slide it back, it slows down. If I advance it forward, the train goes faster. You'll also notice that as I move these sliders, the slider on the web interface moves as well. The two systems are tied together so that you can control control from one interface and move to the other, and the control information is consistent across both. Here's a look at the control interface, the actual program that makes all of this happen. You can see a couple different pieces. I have broken it out into a pretty straightforward set of flows. There's a couple different pieces to it. I'll talk you through each of those, but this is really it. First and foremost, the listener, the HTTP listener for the DX80, its web requests that it generates are found here. There's simply a listener and an HTTP response that replies with a 200 OK anytime a response is received. There's also a select control to change. So this will actually receive two different types of control data. One is the speed, and the other is the actual direction. So if you change direction, that command is going to be processed differently than the speed. Here you can see the change direction process function. We can open it up and see a little bit of the code here. So it's listening for a specific event, and I have to adapt the toggle from an on-off to a forward and reverse nomenclature. When we're done, we can click done. I'm then linking this, the change of direction, down to the directional toggle. So the directional toggle in Node-RED can actually accept an input and be changed as well. I have a delay here for 1 second that will delay the actual change of direction while it waits for the train to come to a complete stop. Here's a function that essentially sets the speed to 0 when the direction is changed, which is tied into the train speed. There's a function to prevent low power. In other words, this is on a sliding scale from 0 to 100. Anything below 30 from an output perspective doesn't generate enough voltage on the tracks to drive the train's motor appropriately, and it just kind of sits there and can't move, and ultimately could cause some damage to the motor if we let it at that state. So that's what this is. It just takes any output less than 30 and sets it to 0. Now this pin, of course, is driving the speed control, and we're using pulse width modulation to then ultimately drive the motor's driver, the 298L chip that is varying the output to the motor or to the tracks, which drive the train's motor. So that is running on GPIO pin 17. We have that selected here. We're using a 100 hertz frequency, and the varying setting, the train speed, is just changing the duty cycle of that output. Down below that, you can see GPIO 27 and 22. These pins are used to toggle the actual, the polarity of the energy coming from the motor controller, and this is ultimately what changes the direction of the train itself.